Hey everyone, so in the first video on first ionization energy, we covered pretty much the basics of ionization energy in terms of looking at the increasing charge on the nucleus, causing an increase in ionization energy, and then as well as, so that's the charge issue, and we dealt, and then also there is a distance issue, which we used part of our understanding of electron configurations to create this effective nuclear charge diagram, and then applied Coulomb's law to talk about charge and distance. In this video, we're going to go over one of the weirdo exceptions to the first ionization energy trends, which is known as pairing energy. So let's just refresh our memory. So there's an exception here that we're going to talk about in this video, which is due to the pairing energy. But let's just refresh our memory first off about the ionization energy trends. So as you go left to right on the periodic table, the ionization energy increases as we go this way, all right? And the reason for that is because we have an increasing, increasing nuclear charge, and you can think of that as either just the nuclear charge or the effective nuclear charge is increasing left to right. Coulomb's law says that greater charge is greater attraction. As you go up the periodic table, the orbitals get smaller, right? So the orbitals get smaller as you go up the periodic table, and Coulomb's law says that the closer that charged particles are to each other, the more strongly attracted they are, and that's why it takes more energy to remove that electron, okay? So those trends are pretty consistent across the periodic table. There's some other hiccups, like when you jump from the 2s to the 2p or 3s to 3p, but we've looked at those. So there is this one important exception that happens in the column with oxygen. This is known as the chalcogenides, which is the worst name ever. It's really hard to pronounce. Anyway, it's the oxygen, sulfur, selenium, etc. column. And this is the column where if you graph the ionization energies going left to right, as you go boron to carbon to nitrogen to oxygen to fluorine to neon, boron is down here, carbon's a little higher, nitrogen's a little higher, and then weirdly, oxygen's a little lower than nitrogen. So sorry, I'm making a crappy graph here of the ionization energy. And then it goes back to normal on trend. Oops, fluorine is higher than nitrogen. So fluorine's up here, neon's way up here. So there's this, it's pretty consistently going up because the effective nuclear charge is getting bigger, and then suddenly there's this dip for oxygen, and then everything goes back to normal. So what's going on here? Well, this is referred to as explained by something called pairing energy. So, oops, and I don't have a page here. Let me add a page real fast. So, when we look at, let's compare the electron configurations for the highest occupied orbitals for nitrogen and oxygen, okay? So nitrogen and oxygen both have their last orbitals in the 2p. So nitrogen looks like this, it's 2p3. Oxygen's 2p4. And the oddball thing about this is this electron right here that I'm about to circle, this one here. So this one is paired with another electron, all right? So whereas the one that gets ejected from nitrogen when we measure its first ionization energy is not paired, all right? So because this electron is paired, the way we think about this is that for the first time in a 2p, we've crammed two electrons, two negatively charged particles, into the same orbital. So they're sharing a lot of space with each other, or they're sharing a limited space with one another. And we know that negatively charged particles will repel each other. And what's happening is that repulsion makes it a little easier to remove oxygen, because that repulsion kind of offsets what would normally be the attraction back towards the nucleus. So normally we'd be thinking for oxygen in terms of our most probable distance diagrams. This is what we would look at for oxygen. And normally you'd think just about the +8 charge of the nucleus interacting with the -1 charge of that final electron. But it turns out there's an added repulsion that we're not considering in our most probable distance diagrams. So this model doesn't work for this because it's not taking into account the added repulsion that comes from having to share an orbital with another electron, all right? So there's some other things going on that I don't want to get into, but that's the kind of the basics of that, just that issue, all right? So we're going to use this, we have to switch models, basically. That screws up my aspect ratio. We have to switch models here, okay? And this is always the case in science. If a model doesn't produce the right answer, we have to switch models, right? So here we have to say, okay, this is weird. Oxygen is not following the pattern. And so now we've got to say, okay, there's a little dip caused in the ionization energy trend, and it's explained by this pairing energy, this added repulsion that comes from putting an electron in with another electron in a 2p orbital. Now, the thing that bugs people is, why does fluorine go back to the normal trend? Because if you go to fluorine, it also would be removing a paired electron. The difference is now you're comparing this paired electron that gets ejected from oxygen with this paired electron that gets ejected. Oops, I drew too many. There we go. So you're comparing the paired electron from oxygen getting ejected from the atom to the paired electron in fluorine getting ejected. So they're both paired. So the pairing energy is no longer a factor in determining which one's bigger. And now we go back to our original model of, okay, here's fluorine. So here was oxygen. Fluorine is 1s2, 2s2, 2p5, right? And now we're back to our regularly scheduled, okay, +9 is bigger than +8. And so the attractive force between the nucleus of fluorine and that outermost electron is greater than is the +8 and the -1 electron for oxygen, okay? So it's only when we have this kind of apples to oranges comparison, when we go from nitrogen with an unpaired electron to oxygen with a paired electron, that we see this dip in the trend. If it weren't for pairing energy, both oxygen and fluorine would have higher ionization energies than they do. However, pairing energy is a real thing. In fact, it's the only validation, or that's not true. It's one of the earliest experimental validations of this model of orbitals that we've just been assuming is true. It's one of the earliest validations that there's something right about this model because it explains for the first time this weird ionization energy dip for oxygen, okay? All right, so I'm gonna give you a quick practice problem here. And I don't have this one set up either. So briefly, I just want you to explain. And notice that a lot of these I'm going to ask you to explain values I'm giving you, okay? So I'm not asking you to predict which ones are higher. I'm going to tell you, explain why, no, I'll stick with that way. Why selenium has a higher first ionization energy than arsenic, even though selenium has a greater nuclear charge. Okay, so go ahead and pause the video, work the question, and then I will explain my answer. Okay, take a few minutes. Okay, hopefully you've had a chance to answer this on your own. And it really helps on these. I know that as a student, it's difficult to practice. I don't know, for some reason it's really easy, or it makes sense to practice calculations. But for some reason there's this like, oh, I don't really want to write the answer out. You have to write the answer out on your own and see if it's good or not, okay? And then you have to revise it to make it better. And then eventually you'll be in such good practice that by the time you get to an exam, it won't be a big deal. Okay, so let's look at, so if we were to draw our diagrams for these, and I'm gonna shortcut this, so I'm just gonna draw the most probable distance diagrams for the effective nuclear charge, because I'm being lazy. If you would like to draw the whole thing out, you're welcome to. You don't really even have to do that, but anyway, this would be the 4s and the 4p3 for arsenic. And for selenium, it would be, oops, sorry, haha, Nope. It's +5 for arsenic. And then +6 for selenium. 4s, 1, 2, 3, 4. Okay, so based on our prior understanding, you would think, this is 4s, this is 4p. You would think that selenium would have the greater ionization energy, right? Because you're looking at a +6 nucleus, -1, versus a +5 nucleus and a -1. More or less the same distance because they're both 4p. Those are not quite, man. These are meant to be lined up because I'm trying to imply that they're more or less the same distance. So something is weird here, right? Because we would have predicted that selenium should have the higher ionization energy than arsenic. And when we run into this, we say, oh, this model doesn't work. We need to switch models. Well, we switch to our orbital diagrams. So for arsenic, it's going to be 4p3, and for selenium, it's 4p4. Okay, and we see, the difference is that selenium has this paired electron, and paired electrons are easier to remove than normal because they're repelled. They're experiencing this pairing energy, this repulsive force that's generated by the fact that they're crammed into an orbital with another electron. And so this paired electron is the one that's being removed versus this unpaired electron. And we know that paired electrons are just a little easier to remove than unpaired, and that offsets the increased attractive force between the nucleus and the outermost electron. Okay, so that's going to explain our this seeming contradiction in the ionization energy. This effect is mainly found in the p orbitals. We don't really observe it a whole lot in the d orbitals for super weird reasons that I'm not getting into. And so it's kind of the one time you have to really deal with this. And it's the one time it shows up really clearly in the data. Okay? All right, so I hope this has been helpful. There will be a third ionization energy question, or video, in which I'm going to do some practice over the more straightforward charge and distance issues in ionization energy to give you some practice. But I know this topic bugs people, so I wanted to make a video just for this one. All right, thanks everyone. I hope this was helpful. If it was or wasn't, let me know in the comments or just get in touch. All right, see you soon.